What's up, everybody? Welcome to Air Science. Today, we're going to take a little bit of a step further with how stars form. And we should review, which you should have just done in class anyway, but we're going to review where we've been. So, if you remember, first we had to form a universe. How did we get that? The Big Bang. And evidence for that includes those two things. And again, the Regents really likes to hammer on these. So, I say it a lot. We're going to want to make sure we get this down. Redshift, the expanding universe idea. Really, the Regents will just be very surface level questions. If you can just keep these two things in your head, you're going to be fine. Just cosmic background radiation. All right, so that gives us a universe. That was about 13, 14 billion years ago. Now, and in the intermediate time, there'd be stars forming and blowing up, and stars forming and blowing up, and in fact, everything that like is in your body and is in this remote control, in this Chromebook, all of those elements had to come into existence through this process of stars forming and stars going away. Um, Before that, we would have just been with like helium and hydrogen, the basic elements that we have, the heavier elements that we use, all formed through this process of stars forming. And that's what we're going to do in today's thing, which is this standard right here. That's the state standard. So now, like 10 billion years later or so, we can form ourselves a solar system where we live. So that's a long time to have passed in between. Like, I'll try to trick you and say, hey, how did our solar system form? And somebody's going to say, I know that, it's Big Bang Theory, but the Big Bang addresses something that happened a long time ago. And then our star formed still a long time ago, but only like 4.5 billion years ago. So let's always get to the beginning of this to get a context for where we are. We are in Pulaski, the village, I suppose, which exists in the state of New York, and we'll just kind of zooming out and zooming out and zooming out. In the USA, on the planet Earth, all maybe things we already know. And then the Earth is part of, we don't really have a name for this. The Earth is part of our local solar system. Nobody ever like named that specifically, like Steve. I don't know. Maybe they should have. But we didn't. Solar system is parts then of our local galaxy, which kind of looks like this swirly guy right down here. Although we've never been far enough away to be able to take a picture of it, which is called the Milky Way. And then since there's a whole bunch of solar systems, there's a ridiculous number of solar systems in this galaxy. There's also a ridiculous number of galaxies in the whole entire universe, which also doesn't really have a name, it's just the universe. All right, so again, this is kind of what our galaxy looks like. We would be one tiny little star on that, and the Voyager satellites we sent out in the 70s have barely made it far enough away from that star. Like, they haven't even gotten close to the next star over. So this view right here, this like selfie of our galaxy, is something that's not possible. We had to look at other ones, look at ours from the inside, and try to figure out about what it looks like. This is about what it looks like. So in other words, we can't do a selfie. You wouldn't be able to like go far enough away from us to be able to turn around and take a picture of yourself. It's just the distances are too immense. But our galaxy is a spiral galaxy containing billions of stars, and there are billions of galaxies in the universe. So this guy came up with this thing called the Drake equation. This isn't super critical for what we'll do. It's kind of like maybe you find this interesting. We look at how fast stars form, and then we like go down. We by like take the tiny number of those that might have planets, the tiny number of those that might support life, the tiny number of those that actually do develop life, times the tiny number of those that develop intelligent life, times the tiny number of those that might send signals out into space. Um, Even though you're multiplying by a tiny number times a tiny number times a tiny number times a tiny number, so we're talking about billions and billions of galaxies. The Drake equation says there's probably is life out there somewhere. It's just so far away that we We don't even have the conceptual framework of how we would make it out there. Not even close. So it's probably out there somewhere. Probably not visiting us uh, in any stretch of the imagination. All right. So how does this work? How are we going to get ourselves a star? We'll start with a thing called a nebula. I was going to look up pictures and be prepared. If you type nebula, you play around with this a little bit if you want to pause into Google Images. Even they're really beautiful looking when they do this style of image with it. There are these interstellar clouds of gas and dust. Notes, notes, notes. Where'd you go? Interstellar just means between the stars. Don't panic about that. Cloud of gas and dust. Very low density. Like you go flying through it, you wouldn't even know you were in it. Really. At some point, and we got to talk about gravity at some point. I don't want to try to cram it in today to do too much, but at some points, if the thing becomes dense enough, and maybe something happened to send a shockwave through it, a supernova or something, where the particles started to come close enough together where they became gravitationally attracted. The short story is that gravity works if you have mass, two things with mass that have a distance between them. The more mass, the more gravity, the closer, the more gravity. So if you get clumps, they're going to have more gravity to pull more clumps towards them, which will have more gravity to pull more clumps towards them, and so on and so on and so on. So it starts to condense things down into a disk. It's spinning, and there's this whole law of conservation of angular momentum, which if you've ever been in anything spinning, you probably realize, like if you're spinning with your on a playground thing with your arms out versus with your arms in, or watch a figure skater do it. Um, those are the basic ways to see like that as something's spinning, this disk thing tends to happen. So like particles in the disk clump together, start to get big chunks of things. And again, this positive feedback mechanism, it's called. The bigger the chunk, the more gravity, the more it's going to pull towards it, that crashes into it, which means it's a bigger chunk, which now means there's more gravity, which means it pulls towards it more, and so on and so on and so on. I could say that forever. So these clumps would get bigger and bigger and bigger and bigger. And it was a very violent time in the solar system. The Earth would have been one of these big chunks, but constant impacts, very little atmosphere to burn anything up. So it's just getting battered all the time. They call it the Hadean period. And if any of you are Star Wars fans, it's kind of like the Mustafar system. Like I think that's what they based it on. If you're not a Star Wars fan, then what's wrong with you? And eventually, as those clumps like go around and around and around and around, and they eventually are going to clean up the orbit. Essentially, now we end up with, quote unquote, clean orbits. Not that we still don't get hit by things, just as the dinosaurs. Um, you get clean orbits, and we still have one asteroid belt. Between the inner four planets and the outer four planets, there's still a chunk of rocky debris through there. All right, so at the end of the day, what we really got to think about here, and what I forgot to mention, what's very, very important for today, is that what's the moment where we go from like some dusty junk in the middle to this giant flaming ball that we call the sun, and it's that there's enough mass in there and enough density and enough pressure and enough gravity to start to do this process called fusion. So our star, the sun, is currently taking two hydrogen atoms, fusing them together into a helium atom, and that releases some energy. That's nuclear physics. It's not easy to understand at all why that happens in Einstein, E equals mc squared, that kind of stuff. But that process, that reaction, is what drives that very violent, out of control, essentially, reaction in the sun that's powering it. It turns it into a star rather than just being a ball of debris. And it's because of the size of it. The sun's huge relative to the other planets. With the other planets spinning around it, there we go. So now we got ourselves a star, we got ourselves planets. Stars change through time. Eventually, our sun will run out of fuel. Currently, its fuel is hydrogen. Got a pretty good supply. We don't have to worry about this happening, but eventually it's going to run out, and it will expand to a size larger than the orbit of the Earth. It will be very, very large. The planet will be consumed by the star, and then everything we ever did will be gone. The HR diagram below, which you guys have figured out the last couple days, categorizes stars as they appear now. But again, through time, stars are going to evolve, and that's what we're going to talk about here. Actually, right here, stars evolve through time. Make sure we're still recording here. I'm not talking to myself. Excellent. So this is kind of like we took it up here. We took it just from like Nebula to Happy Solar System where we live. Let's go further. Cloud of gas and dust, proto star. Proto anything means early version of, like a prototype. So proto star into a main sequence star, and then the higher mass amongst those will go to supergiants. Eventually, following this path, medium mass ones like this is where our sun will end up going down that path. There's another version of it. You do not have to memorize this. That's good news. If the Regents asks about it, this little clip right here is actually from a Regents. I stole that like out of a question. So should the Regents want to ask you about it, they give you this flow chart and then ask you some things. There's absolutely no reason. Unless you're interested to memorize that whole entire thing. All right. But just a quick peek at the HR diagram that you guys played with last week. And again, let's just note that that's now. But through time, our sun, I'll put a yellow dot on it right there. If we follow it, we picked it up into this stage, and there's a question on here later that says about how long things last there. Sun remains for about 10 billion years, it'll be a main sequence star. So we're not quite halfway through the life of the sun, so you're safe. But if we follow this path, that eventually, once that happens in, say, about 5.5 billion years, the sun will stop, it will be done with all its hydrogen, and it will be burning different gases. I shouldn't say burning, it will be fusing different gases, and it will be a giant star at that point. And then there's things that happen, and we can get like, you can go way deep on this. You can do a whole course on it, but keeping it within the level of the Regents and what we want to do after it's done with being a giant. And again, it's another stage in its evolution where it's burning different gases. It'll come down here to the white dwarfs. Other stars take other paths, and really, in case this question pops up, which I'm pretty sure it's going to, the difference is the mass. You all start the same, but the more massive ones take a different branch on the path than the less massive ones. All right, so important points just in case we want to ask some questions, which we just might. Where's my text thing? Stars form because gravity pulls together materials from a nebula. Stars are powered by fusion, and that's squishing together of atoms. Stars have different temps, colors, brightness depending on the, I would say, fuel. I'm not sure it's the best word, but it may be the atoms being fused. Our solar system has one star, which we call the sun. It's part of a galaxy, which is called the Milky Way, which has billions of stars, and there are billions of these galaxies in the universe. All right. Thanks for sticking with me. How long do we last? 13 minutes. Good job. Thanks for sticking with me. We'll try out some questions here, and then I'll have the next question thing for you set up after that. Good luck. Take care.